So the keynote speaker for the morning is Ludwig Otteron. Ludwig is a retired professor from Leibniz University in Hanover in Germany, and he worked for many, many years on dose response analysis. And today, when people it's already made a consensus that you develop methodology and the software together, so this is something that is obvious today, but it was not like this 15 or 20 years ago. And Ludwig was one of the pioneers that understood that the methodology have to come with software so people can use it. And by doing this, he really dominant the area of dose response analysis for many, many years. So, Ludwig, please.
Thank you, Tiff, and thank you to the organizing committee for having 1 hour, first in my life. Up to now, the maximum was 45 minutes. And this 1 hour will be biostatistics. Of course, biostatistics using R. And dose response is an important part of them. First, I'd like to discuss why we do that. And then I look on some nature publications, recent ones, how they consider those, what they mean. And then I come to a lot of statistics, 2 classes, multiple contrast tests and quasi-linear regression models. And the main point is the package TUGE-Trend, recently available in CRUN. And TUGE-Trend is this new working horse. And I will show also that you can use it in epidemiology as well. Outside you will find a poster from the guys from Karolinska Institute. It's exactly their topic, look on that. I try, if the time is sufficient, to explain you really 4 case studies and end up with some communications. What's available in CRUN? Important package by Christian Ritz. He gave a tutorial in the beginning of this conference is DRC. This is focused really on nonlinear models, prediction, model averaging, model selection. Isogene by Ziff and co-workers is order-restricted inference in general for multiple endpoints, particularly for microarray data. And then there's a cluster of packages, dose finding, MCMod, and recently LR contrast. And this is a group in Switzerland and in Germany. And the idea is to combine both approaches. And then there are a lot of other packages, including dose resmeta, where the poster is discussing. And the conclusion is, when I looked through CRUN, we have different tools today and for different jobs. So you can use a lot. Let me come to the nature publications. Of course, randomly selected, I looked through. First example, you see over here, this is a log of any concentration, and then you see what microbiologists like is percentage inhibition versus a control in percentage. And then you see they have a lot of concentrations, and they have one compound, a second compound, and what they are interested is in this additive shift. It's called relative potency. And this problem may be problematic, this assay may be problematic because the dose response shapes are not in parallel. So you can imagine that's hard to estimate additive shift. The second example, again, you see in a logarithmic scale, and then they have really the values of the control. And what we observed, very few sample sizes. Look on molecular biology, sample size 3 to 5 are very common. Not hundreds or thousands. And what we see here, we have a plateau. We have an inhibition, and over 1.6 nanomole, you can do what you want, you are in a plateau. Question is how to analyze this. Next one, all nature publications. Here you see, these guys have any expression level here, and then they have of any compound the concentration of 1, 2, and 4. Okay, so far. But then, they compare to the wild type. It could be seen as a control, but they have other pseudo-controls. There is a mixture of qualitative and quantitative reasoning in dose response. And this is similar in a clinical example here. It's some density, and you have a vehicle control. You have a high dose of 40 milligram of the compound under investigation. You have 10 milligram, and then you have this bar chart is for maybe the competing drug, what's already on the market. That's also very common that you have a mixture of comparisons and trends. It's not just a trend alone. This is a recent epidemiological study, and this is risk of chronic kidney disease, and then they have categorized the analyte. So the continuous endpoints they have categorized, very typically. And there are a lot of papers starting with Greenland in the 90s to show, oh my God, this is a power loss, don't do it. But they do it until now. Why they do it? Because it's nice for interpretation. And here you see a lot of these endpoints, a typical, then they have adjusted hazard ratios. The black one is comparing the third tertile versus baseline, and the dashed one or the gray one, the second one. And so you see it's a brutal, naive categorization, but for interpretation in a medical context, it gives sense. You see, what we learned, power is not the only optimization criteria in this setup. So we learn we have both quantitative and qualitative reasoning of dose. Log transformation is frequently used, and the question is why they do that and how they do this job. It's interesting how in many packages it's done. And what we also see, we have both our regression in groups like 0, 10, 100 milligram per kilogram, and randomly chosen, like in epidemiology. And what we also observe nowadays, multiple endpoints is a standard. It's not a curious situation, and recently high dimensional. We have 100,000, no problem, 1,000 dose-response relationships. We cannot believe that the shape is the same. It's very unrealistic. Okay. The basic model behind all this, I believe, is according to Paracelsus, roughly 500 years ago. And the quote is, all things are poison and nothing is without poison. Solely the dose determines that the thing is not a poison. So if you translate into our terms, it's the classical effect of no observed effect concentration in toxicology. We believe there is nothing, there is a threshold dose, and then is something going up. This is the basic model in all labs in the world, and stated by Paracelsus. The other way around, if you look on the monotone case, not so on the threshold, is Hill's causation criteria. Hill wrote an important textbook on epidemiology, and one criteria for causation, not just any effect, but causation is, let us demonstrate a monotonic dose response. So, what I will explain is, first, I consider dose as a factor. Second, I consider dose as a quantitative covariate or covariable, so like regression. And then I combine both. You will see, this is the first step forward today. And you will see some literature to discuss whether to use a regression or ANOVA methods. There is no a priori best approach. It depends on a lot of things. It depends on the aims. It depends on the number of doses, if you have 2 or 3 doses or 20. It depends also whether there is a big difference between intake of the drug and the concentration really on the target cell. There can be a lot of accumulating effects, so that it's not one-to-one idea. So believe me, I have experience for more than 30 years. It depends on a lot of things, and don't trust that they say, my approach is the best and for all. That's not true. Interesting, Chucky was already cited in the talk before. Chucky has a lot of ideas, had a lot of ideas. And 85 had a brilliant, super simple idea. let's take a linear regression model and take the dose as they are. So arithmetic dose scores. And then make it ordinal, 1, 2, 3, 4, 5. And then do it logarithmic and do something for the distance between 0 and the lowest dose. And then take the best one. That's all. And he used it for estimation non-observed effect concentration. It's, by the way, a biometrics paper. And the interesting thing, I will show you, this simple approach covers most, not all, most of the shapes of dose response. This is one of our objectives, not to see just a linear one or a concave. No, it covers most, including non-linear. It is brilliant simple, and it's easy to interpret. And this is very important, it's just a slope parameter. You can say, if I increase the dose by 10 units, then I have an increase of my endpoint by blah, blah units. And this is what you can interpret also our decision makers, our medical doctors. We are not the decision makers. Okay, the main results are that I show we can combine both approaches. Second, we can extend it in the general linear mixed model. It's very important, and you will see it opens the complete world of real biostatistics problems. And last, the recent research of last week is we can use it in epidemiology as well. Okay, why we do that? Many people analyze just to show heterogeneity between groups. That's a weak outcome, but you will see in literature it occurs. The majority of people, particularly in clinical trials or in pharmacology, toxicology, epidemiology, they compared against the... I'm sorry for that. So, here we are. It compares versus a negative control in clinical trial denoted placebo. And you see the effect sizes, difference of expected value, ranges of expected value, ranges of proportions, etc., etc., etc. That is important. We are open for all effect sizes we needed in medical applications. Some people are happy to claim just a global trend. Yes, there is a trend between age and whatever. Some people are much more interested in the idea of Paracelsus, and they want to estimate the minimal effective dose. That's for efficacy parameter in clinical trials. You increase the dose and you want to know the first one which is better than placebo. Or the other way around, in safety, you want to say nothing, nothing, nothing happens, and then you have a threshold, and this is a no observed effect concentration. Order restriction is a typical way to do that, and here I wrote down. You see, that's simply some inequalities where at least the largest dose group or the effect of the largest dose group should be larger than that of the control. And what is the idea? Most of the people believe we increase power. Power, power, power. Believe me, yes, under some conditions you increase, but the increase is not so exciting. And the price what you pay is we have a brutal trade-off between restriction to alternative and robustness. It's very clear if you would restrict your alternative to exact a linear alternative and it's non-linear, that's not a good idea. Therefore, this objective power is nice, but not for me the most important. Another thing is we want to claim something. And a claim of a minimum effective dose, very important in clinical trials. At the end of the day, the drug will be marketed with this dose. And the interpretation in terms of causation. And here is interesting. Some people for you will work in genetic association studies. And one design is case control. And in this setup, the 90% leading trend test is Cochrane-Armitage test. What is Cochrane-Armitage test? It is a test for logistic regression on a linear increase. It violates my idea that it should be open to any shape, but here it has an interpretation. It is the additive mode of Mendelian inheritance, exactly that. And that is, therefore, its use. 100-fold every day in the world, this Cochrane-Armitage test for a specific, very specific alternative. Okay. You see, there are several motivations, and we have to be careful. And again, I want to show you how simple it is to decompose this general alternative in all linear elementary. And many people have problems to believe that this is a trend. Nothing happens, and only for the highest dose or intensity we have an increase. So it's like a two-sample test problem. It belongs to this. Okay, coming back. If I have not such a specific objective like in genetic association studies, I want to have my trend test should be sensitive against all possible alternatives. That you will never have, that's all. What you can have is most. And it's some crazy, if you look in literature, the two most used tests are Cochrane-Armitage test outside of genetic association studies, and for pairwise ranks, the Jonquier trend test. And these trend tests are formulated, and even in the title of Armitage's paper in 1955, for a linear trend. It is only sensitive for near to linear alternatives. That's crazy. We don't looking only for a near linear alternative. We are looking for a lot of monotone alternatives. Therefore, the most used tests in practice are, for most situations, false classified, false defined. And of course, there are two approaches. We have a maximum likelihood estimation test under this ordered alternative. It's a quadratic test statistics, very old, Bartholomew in 59, not today. Or here, a second one is multiple contrast test as linear test statistics. I will show you in some slides the basic idea. And if you see, the most used test is Williams contrast test. It's very typical in non-clinic and clinical dose finding. What is the basic idea behind? You defined a contrast. A contrast is a suitable linear combination of means, but be careful. It's not only for means. It can be for any estimates, hazard ratios, proportions, what you want. I will show you some later. That's important. It's a very general approach. Many people believe it must be arithmetic means. It's not true. Okay. Then you standardized, studentization, and the sum of the contrast coefficient zero guarantees that's a univariate level alpha test. And if you want to have compatible simultaneous confidence intervals, you have a second condition to consider. So, and then we have some of these tests, not only one, because we have some possible alternatives, and we take simply a maximum. Maximum of T1 to TQ, you will see in a minute in a slide which one, how many, and which one. But important is that this univariate test statistics follows jointly a Q-variate T-distribution, Q, number of included tests, with a common degree of freedom. This is our well-known degree of freedom of the ANOVA, and a correlation matrix R. And this correlation matrix R depends in simple cases only on the contrast coefficients Ci and Ni, but in real problems also in much other estimators. And this is one of the serious problems. This correlation matrix may be simple, like Dunnett procedure published in 1955, or may be rather complex. And our research was how to handle this complex one. Okay, and the story ends to say which one we use, which test defines the particular test statistics. So, first one, Dunnett procedures. And you see here's a typo, it should be +1. You have a contrast, treatment 2 versus control, and treatment 1 versus control. Very simple. Or Tukey test. It's all pair comparisons, two-sided per definition. Or change point contrast. You have a change point here between control and dose 1, and you have here a change point between pooled control and dose 1 and dose 2. And you don't know where change point, and therefore you use both. You have only 2 test statistics in this case, and take the maximum. And the rationale is there's only one the best. It cannot be all the best, only one is the best. And the Williams procedure, you see the idea behind. You have a first contrast, you compare control versus high dose, the same like done it. But the second one is you pool the higher doses. Here we have only 2, and if I'm more, then you have more contrast pooling the doses. There are much more. Literature is full of this multiple contrast, increasing ground mean, etc. But you see, it's one approach, and the special cases are only different formulation of the correlation matrix, full stop. And important is that we have compatible simultaneous confidence limits. Here written, you see the formula is very simple. Here for a one-sided one, you have the variance estimation, then you have your Q-variant T distribution with a common degree of freedom with a correlation matrix, in this case defined only by Ci and Ni. That's wrong, one-sided, and the adjustment for the variance. That's all. And of course you can use multiplicity adjusted p-values. Now, this is the status about 20 years ago, all is known, but now, why we should use only difference of expected means? If you look in textbooks for biostatistics, this is described as the standard. And people believe it's the only what you can do. No, it's not true. You can do it for ratio as well. And believe me, a multiplicative model gives something much more sense instead of an additive model. It depends on your objective. And already 40 years ago, Sasabushi has the trick. He reformulated the ratio into a linear form. So we are back in our theory. Feiler, 50 years ago, already realized it comes to a quadratic test statistics in that form. But the problem comes now. This correlation matrix depends now on the unknown ratios. What we do in statistics, if we have unknown, like unknown variance, we take the maximum likelihood estimator by the data, plug in, estimate our confidence intervals, and then we go back. And this second trick works perfectly, even for very small sample sizes. Not surprising. It's supported by statistical theory, but it's very important, this second trick. And there's a package since 10 years, M-ratios, and this contains not only this idea, it's much more general, including mixed models. You can analyze relative effects versus control, or whatever you defined. It's open. You can use any contrast definition in the mixed model. Notice, if you look on literature, pharmaceutical, statistical literature, what people are doing, log transformation. They want to come with a log into a multiplicative model. This works as long your error is really log normal distributed. If not, good night. That's not a good idea. It can be very biased. Here's a nice paper some years ago showing how problematic this is. Next topic. Have you ever seen real data which are really homogeneous variances? I am not. The standard in practice is that we have not only an effect in location. If some drug is acting, we have also an effect in scale. Moreover, we have also effect in higher moments, not considered here. So we have to consider at least treatment or dose-specific variances. And at the end of the day, there are 2 approaches possible and needed. The one idea you know from Welch test, the idea is the larger the differences between the ratio of variance to sample size, the more you shrink the degree of freedom to keep a level alpha test. That's Welch idea, or in a more general setup like here, satellite. That works perfectly. It's a little bit conservative if the variances are equal in a balanced design. But the problem we have to solve that now the correlation matrix of our multivariate T distribution depends not only on the ratios, but also on the unknown variances. The same story, maximum likelihood estimator, plug in, estimate your correlation matrix, estimate the confidence intervals. This is in this function in M ratio. An alternative, of course, a sandwich estimator works also perfect. However, it needs large sample sizes. And so about 20 above. And in particularly in toxicology, 20 above rarely occur. Therefore, we focused on that. Another effect size. You know, many people like rank tests, like Jonker test. What's the problem with this test? In ordered alternatives, we formulated this alternative for distribution functions. However, the distribution of the rank means is unknown under the alternative, only under the null. And many data have tight values or even order categorical data. And you know, Wilcoxon type statistics are only corrected for ties. They assumed any continuous distribution, not a discrete one. All what you find in software, in R, in SRS, it's only an approximation. And if the number of ties or the percentage of ties is high, good night. The other problem before, variance heterogeneity is not a curious situation, it's a standard. So we have to use a test statistics which is robust for the situation of variance heterogeneity. And believe me, the Wilcoxon test is not robust, and the Kruskal-Wallis test is not robust, and the Jonker test is not robust, described in literature. And some years ago, people introduced a new effect size. It's a relative effect size. You see, it's similar to the Wilcoxon test, but it's not the same. And if you look carefully, it's like a win probability. It's a parameter concept by Hayter, now used the probability to win in a clinical trial, your personal percentage advantage over a competitor drug. It's also a nice effect size, not the difference of expected means. And simultaneous confidence intervals can be easily estimated. If you estimate these relative effect size estimator for control versus any dose group L by the ranks, you see it's easy. And asymptotically, it's important, this follows a central multivariate normal distribution with a covariance matrix what we can estimate. And this is available in the package nparcomp. You see, known parameter comparison. And again, you are free to formulate your contrast matrix. You can do what you want. It's just a framework for multiple contrast with relative effect size. Notice, this test is asymptotically correct for any discrete distribution. It's for any shape of the distribution, including variance heterogeneity, which all competitors are not. So it's a relative robust version. Proportions occur permanently, tumor rates or severity rates, whatever. And wall type, it's very clear. I described already before. It's simply a different effect size, difference of proportions. However, we are focused to small sample sizes. And there are some approaches. Two we realized in the package MC-PAN. One is profile likelihood, and the other one is very simple. It looks like stupid, but there is some theory behind, proposed by Agresti 20 years ago. The idea is you add to the success and you filter one cell, one value 1. And so you biased a little bit the test statistic, you shift it, and this guarantees coverage probability of 95%, even if sample size are small. Small, I mean 20, 30 or something. And we are interested in pharma research frequently in one-sided alternatives, then it's better to add only one, not two, a half to success and a half to failure. This is, by the way, also available for risk ratio and odds ratio, and simultaneous available in the package MCPAN. So here it's described how it works. You see contrast definition of a proportion. Here is a difference of proportions. Now we have not a T distribution, we have a normal distribution. The correlation matrix depends for correlations only on C and R. And then you add a little bit and you have tilde estimators for add 1, 2. It works for practically rather good. And it goes on. You can use it for hazard rate and Cox proportional model. You can do it for multiple endpoints. You can do a lot of things because it belongs to linear mixed or generalized linear mixed model. Okay, half of my time is gone. It's good now to switch to dose as quantitative covariate. Now I forget that's a factor. Now I come to regression modeling. So again, the proposal by Tjuki was take the dose as it is, transformed ordinal, transformed logarithmic, take the maximum. The problem is at that time they had no idea how to describe this maximum. And here is the formal version. If we have some clinical endpoints, not only one, it's not only for univariate, you can it formulated for I multiple endpoints. And of course, you have Xi models, 3 models. Xi is 3, arithmetic, logarithmic, ordinal. And you can estimate very simple this marginal model. And you can perform a simple test on the slope. Is this or are these 3 slopes, maximum test, unequal to 0? You can formulate it one-sided if you like. And this is a union intersection test. So the Copenhagen group published some years ago a multiple marginal model approach. And here we use marginal models, or exactly our marginal model, Xi, or I Xi. That means if we have 3 dose meters and I endpoints. And important is that in this framework, the correlation matrix is estimated. I must not calculate it in advance. And the joint distribution of these parameter estimates for multiple marginal model can be achieved without assuming a multivariate distribution of the data. Very important. It's a very limiting fact that many approaches like hoteling assume that the data are multivariate normal distributed. This function is available MMM in the package Multcamp. And the first step is derivation of these asymptotic representation of the parameter estimates by derivatives of the log likelihoods. And then you plug in, and at the end of the day, you have an empirical estimation of the variance covariance matrix. That means these covariance matrix estimated based on function of the data, not on the data itself. Remember, I have models. It's not the data. So, and then I can use these parameter estimate, and at the end I have a sandwich estimator. And so I can estimate the correlation between my parameter estimates from different models if I fit to the same data. So the data matrix must be the same. I cannot switch the data, sometimes the problem. But I have multiple models on the same data, and then I achieve the correlation matrix. And that means by using this approach, it is possible to formulate maximum tests on multiple models, here multiple linear models. I will show you it's not restricted to linear models only. And at the end of the day, we can estimate adjusted p-values for these multiple inference or simultaneous confidence intervals. And the important sentence is without the explicit formulation of the correlation matrix. And that works in linear model, in generalized linear model, in linear mixed model, and in future also in generalized linear mixed model. However, only asymptotically clear. It's an asymptotic approach. That's very important. That was a step in my research when I realized this problem, because I failed sometimes to formulate complex correlation matrix by calculus. Okay. You know, in research we are focused to small sample size. The question was how we can do that. Very simple. If you have an appropriate chosen degree of freedom, not so easy in mixed model, believe me, not so clear. In linear models, very simple. Then a finite version, simply switching from a multivariate normal to multivariate t-distribution, works very well, down to sample size 5, if you like. And this is used in the package, and I will show you now how it works in R. This is an example in toxicology. You see we have dose levels. This is a control, several others, and the high dose is 1,000. And each rat has a body weight, and then it will be sacrificed, and the liver weight is also obtained. You see, we have a bivariate, normal distributed endpoint, and we have a quantitative dose. What we do now is we formulate slope to zero hypothesis for these 3 dose metameters, arithmetic, ordinal, logarithmic, and the 2 endpoints. What I do, 6 correlated tests on slope parameters, and they are highly correlated, you can imagine. Body and liver weight is correlated, and the 3 dose metameters are correlated. So the penalty you pay to consider more than one model is, but it's not too large. So now I hope you have the chance to see my code. This is the first elementary model. You see, I have the dose arithmetic and the liver weight, dose ordinal and the liver weight, dose logarithmic and the liver weight, 3 linear models. And the same for body weight. So I have 6 elementary models. Then I use Multcom, generalized linear hypothesis test, MMM, and then I plug in these 6 objects, and then I defined here testing slope versus 0. It could be also slope versus 0.5 if you like, but we test against 0. And in the object body contains, if you use summary function, the adjusted p-value or conf int, you have the confidence interval. In the package QK trend, it's a little bit easier, but I show you for didactical purposes that you understand. We have really 6 marginal models, and it's your job to formulate the 6 marginal models, and the job of our approach is to estimate the variance covariance matrix and following for the 6 slope to 0 test the confidence intervals or p-values. Here you have the 2 marginal models, one for liver weight, one for body weight, and then you have a function QK trend fit. You plug in this object, and then you can choose the scaling. Arithmetic ordinal, arithmetic log. You can choose several ones, not restricted to this. And then you have the 2 ones, and then you combine by this function compt, and then again within generalized linear hypothesis here in this object you will find the adjusted p-value. You see it's numerical, very simple. Let us interpret. That's a little bit nasty, simply copy and paste it. And what we see, all are under alternative. And the most, here by the test statistics or by this tiny p-value, the most extreme one is just body weight. So that means we have both a decrease in body weight, we have both a decrease in liver weight, and it's according to the untransformed measured values in a linear regression model. That would be a nice result for toxicologists. Important is this remark. Of course, I could start with nonlinear models, with splines, with polynomials, with whatever. We have all toolboxes full, and to find an optimal fit. But this is not my objective. And the price we have to pay is we need more than one parameter. And this makes so complicated later on to rank or to compare multiple endpoints. Remember, we have hundreds or thousand multiple endpoints. At the end of the day, we must rank them. And if one is formulated in the Emacs model and the other one in a beta-Lanafi model, two nice nonlinear models, maybe the best for this endpoint, you can't compare. It's apple and pineapples. Here you stay in the same simple one. And remember, Mr. Box, all models are wrong, some are helpful. That's very important here. It's not objective, the best optimal fit. So you see, power or best fit is not the only objective we have. Now comes the step forward for me. I can consider both simultaneously. I can use a qualitative factor and a quantitative covariate. Previously, in the literature, are complete two boxes. Nobody has published, or I didn't found it at least, a joint approach. And here, it's very simple. We can do it simultaneously. For instance, arithmetic ordinal logarithmic and the Williams contrast test. And the background for that is that the correlation matrix is estimated by model formulations and the data. You must not calculate, which is not feasible here. I cannot do that. And then you can combine any model in a framework of linear models. And a factor is any model, and a regressor is any model, and you can combine. And this allows you nice interpretation. I will show you in an example. Again, example from toxicology, liter weights. Here you see it's a slightly unbalanced design, 0, 550, 500. You see this logarithm dose choice is in the mind of these toxicologists. And the question is there any decrease? If you look on the data, not so clear, but we see it's some plateau here. We don't know already. It seems to be from the control, we have some decrease, but here's a plateau. Really a trend, I can't see. How we can analyze? And now I use 4 marginal models for 6 hypotheses. 3 regression models for my arithmetic ordinal and log linear, and 3 Williams type multiple contrast. Very easy here in the Tukey trend function. You can say arithmetic ordinal arilog and treatment. Treatment is a nickname for factor. And then you can define your contrast type. You see, again, it's open. You can use the entire world of contrast, not necessarily Williams. Williams is here predefined, but you can write also any contrast matrix, what you like. And then you have the combination of regression and factor. And look on here. Again, copy and paste, not nice. This is arithmetic ordinal logarithmic regression, and the contrast 1 for Williams is comparison to the high dose. Contrast 2 is comparing the both high doses, and contrast 3 is pooling all 3 doses, comparing versus a control. Going back, Williams compared first contrast C1 is 0 versus 500, 0 versus pooled 50 and 500, and the third contrast is pooled 550, 500 compared versus control. And what you see? All my regression models fail completely to show any alternative. Not surprising if you look on the shape, but one of the two-sided here, should be one-sided. One of the contrasts, namely this pooling contrast for a plateau, shows you an effect. So now we have a not clear formulated question and answered it by 6 elementary answers. Very different. However, they are highly correlated, and therefore the penalty not only to consider the doses or only consider the contrast factor only is really a penalty. You can do it simultaneously, and the important thing is in this function the joint variance-covariance matrix is estimated. This is a step forward. Look at many plateau shapes, And if you run with some models, you may have serious problems. Okay, a little bit more general. Williams qualitative, Tukey quantitative, Tukey and Williams both. And you look what happens. If you have a linear true alternative, then of course Tukey has a higher power. If you have a plateau, of course Tukey will fail, and of course Williams will show a high power. If it's sublinear, of course Williams will have not a good power, Tukey will have power. But look on that. That's an average power. It never fails, and it never has the best power. I think this is a good choice for practical solutions. So I will skip here, look on the vignette on the package, and you will see a lot of generalization for non-monotonic one, for multiple endpoints, etc., etc. I look here a little bit on the time. It works in GNM as well. It was in rank regression. You can use this for meta-analysis and exposure epidemiology. You can use this in mixed effects model. And this is what I want to show. Many designs in pharmaceutical research have technical replicates. And the analysis is mostly naive by averaging the technical replicates. But we know mixed models are available. We can use it. I show you a known clinical example again, where the replicates are natural replicates, and in this box plots I will explain. This is 0, 30, 75 milligram per kilogram any compound. And here you see the box plots, and the individual dots are the single pups, and you know within a litter, this is the first female, and within a litter they have different pups. Characterized and to be female and male. And you see, it is not good to average overall. You should take into account this litter structure as a random effect. Easy job. You see, we use LMER, and we use a random effect litter here, very, very simple formulated. This is possible by this function, by Christian Jutz, and it will be available in a recent biometrics paper under review. And you see, very simple, it works to estimate p-values or confidence intervals by plugging in these objects. Of course, asymptotically only. This is what I like, this example. Coming back to the organ weight example, and we have the problem, should we consider organ weight alone, organ weight adjusted by body weight, which many people do, so-called analysis of covariance for one covariate, or what toxicologists do, relative organ weights. They take simply liver weight divided by body weight as a new endpoint, relative liver weight. What I'm doing is the following. I take my marginal models for liver weight, only liver weight. For relative liver weight, is a special ratio function to include body weight. So I switch the endpoint, or liver weight, dose plus body weight as a covariate. And then I plug in my objects here, perform Tukey trend test, combine both, and then I estimate confidence intervals, or here in this case, the adjusted p-values. And this is important. It looks really strange. We should improve it, but simply copy and paste. And you see here, my three models, arithmetic ordinal log, blah, blah, and then only liver weight, relative liver weight, and liver weight and body weight. And if you look here, you see the best model is to consider only liver weight, not adjusted by a baseline covariate, important notice, taking only the arithmetic doses into account, linear regression. That's the best what you can find. What it means, this is a mechanism behind. That means the mode of action is not going over body weight. You know, a drug can have an action on body weight and on organ weight, or directly. It has a special meaning. And if you look on clinical trials, phase 2 clinical trials, they have a lot of baseline covariates. And they do it routinely by covariance adjustment. That can be misleading, that can be biased. And one possibility is to say, okay, I don't know, let me formulate it all, take the maximum over this, select the best one, the idea is which is most in the alternative, and pay in price. These p-values are not Bonferroni adjusted for these 9 models. They are less conservative as Bonferroni because you have the feeling all these models are highly correlated. And if a multivariate distribution, or the quantile of a multivariate distribution, and the correlation matrix tends to 1, then you approximate a univariate distribution. That's the whole story behind that. Okay, my last example, I look a little bit on the time, is we have not only normal distributed multiple endpoints. This is what you find in statistics in medicine every week, a lot of nice approaches, but they assume they are all normal distributed. No. Our endpoints comes from, for instance, normal and binomial, binomial and time to event, Poisson and normal, whatever. And you know, there are a lot of approaches to handle this, some from Belgium. And I show you again a reprotox example, and my litter weight, it's relatively likely to be normal distributed, but also we take account how many litter mates are in this female. You can imagine if there are only 2 rats, 2 young rats, or 20, that should have an impact on the liver weight. So you can analyze as a bivariate problem, however, then you have a Poisson distribution, however, and then you have extra variability, so overdispersion between the females within a dose group. No problem here. I show you the elementary code. Here you see my linear model for weight, dose, and gestation time as an adjusting covariant. Then my trend fit. Then here a GLM for a number of pups, same or similar model with quasi-Poisson link function. And then to combine both, and what's going on here, we have a simultaneous inference of the bivariate problem with 3 possible dose response model, and the outcome is nice for toxicology, nothing. So it seems to be safe. Okay, I have 9 minutes, and I will skip this. You can use it also for multinomial endpoints. Send me an email, I'll send you of this slide and more. I want to discuss this because this is very common. Here are the data of a cross-sectional epidemiological study. And they want to know the association between age, you see here age, and any metabolite analyte. So normally this endpoint is 500,000 or more. And then you see this association, and it looks crazy. And associations, they translate in a monotone relationship of a shape we don't know. What you see, maybe there is no association, looks strange. And what you see here, a lot of values here are on a threshold. Very typically, if you analyzed body parameters, then you are on a threshold, and this means we have a mixture of any distributed endpoint and left censoring. So you don't know what is the true value if the values are so small. Okay, question is, can we use the Tukey trend test? The answer is, yes, we can, hopefully, because this is a snippet of a simulation study. You see, I choose a very tiny sample size of 10. Then we have 4 doses and 1,000 runs only because this package needs a lot of computing time. And I explain what we compared. This is the nickname for Tukey. It's a maximum of linear regression, log linear regression, and ordinal regression. This is a nice paper recently in biometrics and the package LR contrast. It's a similar idea, but now for known linear models. And here I use a maximum for linear, log-lin, you see, Emax and exponential. This list is really also in the package LR contrast as a list, can be chosen from all the known linear models available in DRC by Christian Ritz, this package DRC, A lot of models, I guess 20 or so, or you can write your own. So we did not, we choose this one. This I explain later. And the first what you observed under the null, we don't really control alpha. It's a little bit liberal, not surprising here. I can tell you if sample size is 30, wonderful, 5%. But I want to demonstrate that this is an asymptotic approach. And then I have the true alternative lin, log-lin, and Emax. This is really a known linear one. And what we see, it's not surprising. If I have a linear true alternative, then this maximum test has the highest power, a little bit higher than here. On the other hand, if it's log linear, even the Tukey test have the same or a little bit higher power than the maximum test for nonlinear models. And if you have an Emax model, which is quite complicated, you see, of course, here the power is the highest one, but the power loss for a naive model, notice, maximum on 3 transformations, is nearly the same. So that means, of course, if you are eager to have the best fit, most powerful dose response, use nonlinear models, and you run into the problem which one you select here. But you can do that, no problem. But you pay the price for that you come out with a lot of parameter estimates when you cannot compare over different conditions, different endpoints, whatever. So the message is Tukey test excels by its easy interpretability. Notice it's just the slope and generalizability. You have seen GLM example and mixed model example. It is much more. And what is here? This is what epidemiologists like. They categorize the data. You have age, and then you make categories, like Tukey's Fifnium. This is minimum, maximum, 25, 27, 50% quartile, and then you form classes, and then you do it on these classes. And you see what is described already Greenland 30 years ago, not too a good idea, from a perspective of power. If you are intended to interpret, maybe not so bad. Okay. More than these applications for multiple marginal model, we are able to have multiple normal-distributed endpoint in multi-arm trials. We can analyze easily multiple binary endpoints, again, in multi-arm trials. This is very interesting. This is a generalization of this Cochran-Armitage test. We can, of course, use for each mode of inheritance, recessive, additive, dominant, or whatever you have, or not only the 3-1, you can formulate models, transformations, take the maximum. Disadvantage is it takes some computing time, not for a genome-wise association study of 1 million SNPs. We can use it for composite binary endpoints, subgroup analysis where you claim total targeted and complementary simultaneously, which is interesting for some users, will be soon. And interesting is also that some clinical trials have repeated times. And normally they put the time, they repeat it into a variance estimator in a linear mixed model. Here we make inference on both dose, that's independent randomized, and time, that's dependent, and we estimate the variance-covariance matrix. Very interesting. You can make an inference on both simultaneously. Coming to an end, trend tests for several possible shapes are available. Within, it's important, GLMM framework. You are open to do your work. And this is rather relevant for non-clinical, clinical trials and epidemiological studies. You have seen the combination of factor and regression can be recommended because it's never powerful, the best one, but ever stable. And the library is very simple to use. And the important point remains you interpret slopes. And remember, medical doctors are the decision makers. You can extend to regression type 2, means random one. The flexibility was also for me amazing when I wrote a vignette, so about 20 examples. Use confidence intervals if possible. What's needed in future is really a comparison to nonlinear models, not only Eller contrast. You can imagine you can model averaging or model selections. There are several ways to run. And remember this talk, the basic property of multiple marginal model is you can formulate based on marginal models a lot of things, and you must not formulate explicitly the correlation matrix. This is painful. And the last comment is this approach follows KISS. Keep it simple, stupid. I think it's important. If I come out with a random forest and give them a medical doctor, he will be happy about these nice figures, but he will never understand this. This slope you can translate in words for medical doctors that you have a feeling what it means. Thank you for your attention, and here are full of references.
Thank you very much. We have time for a few questions. Are there any questions?
You shortly mentioned multiple endpoints, and I'm a bit confused about that because in my experience, multiple endpoints always implies a medical decision on what the priority of the two factor is. If we apply to the ethics committee, they will say, what's the safety against efficacy, or what is the quality of life against life duration? Can you comment on that, why you can...
Sure. This is here the situation where all endpoints have equal meaning. Yeah? But of course, you can have an a priori prioritization, and then you can use different techniques. For instance, you can define a primary efficacy endpoint and secondary safety endpoints, and then this analysis is not suitable. You have to analyze marginally and then to take, for instance, a step-down procedure, so like Bonferroni generalizations. Sure, that's a different story.
More questions? Okay, so... Oh, sorry.
No, we...
First of all, I almost never say thank you for a talk, but here I say it, thank you, because we have similar questions very often where we don't find effects because it's somewhere in between and we don't know where is the step. And the question is if you take a gradient design or organize the contrast differently. So that's really a nice thing to hear this. But then we have also another question where we try to describe the behavior, indeed with nonlinear models. And the question is, I know you didn't speak about this, what is then the path to go to the next step to describe it? Yeah, because I'm working in environmental modeling, and so we need the intermediate things, not only the endpoints.
Okay, clearly that would be a second step. If I have 1,000 endpoints, I filtered, for instance, 8 important, and then I would start with very detailed analysis, fitting the best nonlinear model, figuring out, discussing the parameters. The problem is we want to have a screening for quite different dose response first. Then you have to do a second job, no question.
Okay, thank you very much. This is now the time for coffee, so thank you very much. Let's thank him again.